All right. Good morning, Ting. My name's Andrew Medina with Group 6 from Aerospace Design 2. Today, we're going to be discussing our austere field light attack aircraft, the G8R or the Gator. Next slide, please. So a brief overview of the two missions that were in the proposal for this design request. The design mission, which is the fully loaded mission of the aircraft with ordnance and such. So you've got your warm-up, takeoff, climb, cruise, and then a descent to the battle space, 4-hour on-station time, a climb back to a safe altitude, cruise home, and a landing. The ferry mission is pretty straightforward. It's just from one airfield to another. Some of the design requirements, 30,000 foot service ceiling, takeoff and landing over a 50-foot obstacle in less than 4,000 feet from runways at 6,000 feet density altitude with semi-prepared runways carrying up to 3,000 pounds payload. Next slide. It's a brief overview of the aircraft, some highlights. Powered by a Pratt & Whitney PT6A-68C, making 1,600 shaft horsepower, 11,823 pound gross weight, max speed of 350 knots, just over 3,000 foot takeoff distance, and just over 2,500 foot landing distance, and just over a 1,000 nautical mile cruise range.
So prior to any of the design work happening, there had to be some research for similar aircraft. So we included a table here of several different light attack aircrafts that we thought were similar to what we wanted to design for our aircraft. So we have the A-29, the P-51, the T-6, the EMB-312, and the AT-802U. In particular, we focused a lot on the A-29 because a lot of the characteristics and parameters of the A-29 were what we thought would fit the design requirements for the RFP early on in our design. However, it was just a baseline model for our design because there were a lot of limitations in the A-29's design, which we'd have to overcome in order to fulfill the requirements that were listed in the RFP. So after the similar aircraft research was accomplished, the first step in the design work was doing a preliminary sizing, which was determining a number of initial parameters and factors, such as you can see on the screen right there with takeoff weight, lift to drag ratio, and max wing loading and everything else. And these are important because it would carry on to the rest of our design and kind of mold how our the rest of our subsystems and how our aircraft would actually look down the line. So on the left-hand side, you can see an example of this for the takeoff weight. We included a MATLAB script of the iterative process of finding the takeoff weight. And you can see that a lot of different parameters and values are used for the A-29, as well as different historical data given from the textbook. And then on the right, you can also see a trend line that we used from the similar aircraft from the previous slide to determine the takeoff weight over the empty weight fraction.
So for the airfoil selection, we started off by finding the ideal and maximum lift coefficients. And to get these values, we use the cruise speed, stall speed, takeoff weight, and wing planform area that we had calculated previously, and then performed a trait analysis on the aircraft that you saw earlier. Then once we got their airfoils, we used X-foil to analyze them over a range of angles of attack, and we were able to compare different parameters, different aerodynamic characteristics, such as the lift coefficient, which you can see a plot of in the top right, a few different airfoils. And once we analyzed these airfoils, we then were able to interpolate them and create an airfoil that fit our needs more ideally. So then once that was interpolated, we reanalyzed the data and were able to choose the NACA 6413 as the best fit with our requirements. You can go to the next slide now.
The primary considerations while designing the full wing were reducing the drag, the weight, and the manufacturing costs.
This process was done mostly in XFlare 5, which is an envisaged flow solver, which supports 3D wing design. From this, we were able to find the expected lift coefficients and drag coefficients as a function of alpha. The wing tip is 45% the size of the chord length compared to the root. This increases the aspect ratio of the wing, which in turn helps reduce the drag due to lift. The NACA 6413 is used throughout the entire wing cross-section, which reduces the manufacturing cost compared to having multiple cross-sections. A dihedral of 3 degrees upwards was added primarily to increase lateral stability. The root of the wing is mounted horizontally with the aircraft body. However, since the airfoil selected is cambered, there is still a 0 angle of attack lift, such as during takeoff. The wing is also twisted by -3 degrees at the tip. This reduces the chance for flow separation towards the tip during high angle of attack maneuvers. And the final wingspan is 46 feet with an aspect ratio of 6.35 and planform area of 333 feet cubed. Next slide.
Morning, everyone. I'm going to talk about the propulsion system and the landing gear. So we set 6 pre-designed considerations that helped us choose the main engine type. These pre-designed considerations are here on the left. The first 2 were set by the RFP, and the last 4 were set by us. We ended up choosing a turboprop engine. We believe this is the best design for our mission for several reasons. I'm just going to mention a few. The turboprop engine is just more capable of withstanding grass, dirt, and foreign object debris that our aircraft will be subjected to due to the austere field requirement. Also, turboprops allow us to shorten the takeoff and landing distance, which is also one of the hard requirements set by the RFP. In terms of reliability, fuel consumption, and operations and maintenance costs, if you compare a turboprop to a jet engine, it has all of these advantages in comparison. The overall costs are just much less, and we do not really have the high speed requirement or the very high altitude requirement to justify a jet engine. So for all those reasons, we chose a turboprop engine. We selected specifically Pratt & Whitney's PT6A engine line, specifically the 68C variant, which is a 1600 shaft power turboprop. This is a very reliable engine. It's been in operations for many years, and for those reasons, we think this is the best engine for our design. Please, next slide. So for the propeller, we chose a 91-inch diameter, 5-blade composite propeller made by Herzl. The first thing we did was to calculate the diameter range for the size, and we selected a propeller that would fit that size. You'll notice we chose a composite propeller, not the more common aluminum propeller type. This is due to the advantages that a composite propeller would give to our design. The most important ones are a reduction in weight. This type of propeller would allow us to, this type of structure, would allow us to construct a thinner airfoil, which in terms increases the efficiency of the overall propeller, allows us to increase the number of blades. This reduces vibration and noise, increases the lifetime of the engine by reducing engine wear and tear. According to the manufacturer, this specific propeller would give us a 10% increase in takeoff acceleration and about 2 to 5 knot speed increase during cruise, and this is comparing it to the aluminum counterpart. In terms of performance, this specific propeller in combination with the engine would generate close to 1,500 pounds of thrust in level flight, and that's accounting a 20% efficiency drop. Please, next slide. So for the landing gear, we studied different configurations. We had to eliminate some due to stability concerns and operations and performance concerns, specifically during the takeoff and landing from austere fields. So we ended up choosing a tricycle nose gear setup. We believe this is the best setup for our design of the mission. This specific design will feature all the pneumatic shock absorbers, a retractable mechanism. You can see on the left the hydraulic retraction mechanism. And on the right side, you can see you'll see some information about the maximum loadings that the gears will experience, and also the tires that we selected. These tires are type 3 tires, which are lower pressure. We think they are better suited for the austere field operations. Next slide. Thank you.
So for the fuselage design, we decided to go with a semi-monocoque structure. This is the most common structure among commercial and military aircraft because it really provides the structural integrity needed, as well as a low weight comparison to the monocoque structure or other structures such as the truss structure. And for military operations, that structural integrity is definitely necessary, even if the fuselage is not going to be receiving all of the loads. So as you can see here, there's pictures that have a combination of longerons and frames, and trade studies between the different aircraft we mentioned in the beginning were used to find the distance between each frame. And that distance is about 2 feet right now for the frames and 1 foot for the longerons. And for the materials, we'll be using 7075 T6 aluminum for the frames and longerons, and 2024 T4 aluminum for the skin. On the bottom, you can see the picture on the left has the skin, and the picture on the right is just the frame. And it's not shown in the pictures here, but the stringers will be used to prevent tension and compression for bending. But we didn't want to overcomplicate these pictures. As you can see, they're already quite full. And the dimensions are shown. It's about 5 to 6 feet wide in most sections, and the maximum being 6.8 feet. And the entire frame is 37 feet long with an additional 2 feet from the cap. You can go to the next slide, please. And for the tail design, we really focused on a simple tail design to get enough stability that we needed for our system and make manufacturing nice and easy to lower the costs. So that equation in the second bullet point were the two equations used for calculating the areas of the vertical tail and the horizontal tail. And then these areas plus historic data and trade studies from the other aircraft were used to get additional parameters. The table on the bottom right has a list of parameters for our tail design, and the picture on the top right has the dimensions as well. We also added 2 ventral fins and a dorsal fin, which can be seen in those images. And the ventral fins will help with spin recovery and also provide a little more lateral stability, which was necessary for our design, as the location of the horizontal tail is at that mid-level and is a little more, the airflow is a little covered. And the dorsal fin will help at higher angles of side slip because, as you can see, the horizontal tail also does intercept the vertical tail location slightly, and so the effectiveness of those control surfaces needed to be improved using a dorsal fin. You can go to the next slide.
So this is a rough overview of the general layout of the crew station. 13-degree seat back angle, which is standard for ejection seats. 130 inches in length and 48 inches wide, and optimized for sitting height of 44 inches, which accommodates the range of sitting heights, minimum maximum sitting heights per United States Air Force standards. There's also a 30-degree overnose angle to aid pilot visibility for descents and landings as well.
Initially, a cantilever beam was used to analyze, and that was using Euler-Bernoulli beam theory, and this was positioned at the quarter chord point. The force on the beam was assumed to be an elliptical lift profile, as shown in red, which is equal to the weight of the aircraft. Taking the integral of this is the shear force, and then the further the moment of the beam. As expected, the highest stress point is going to be at the root of the wing spar, specifically at the bottom. The graph on the right compares the tip displacement versus the spar moment of inertia. This, along with a safety factor, gave a bounding estimate for the root spar around 0.0002 meters to the fourth. This analysis was extended to SolidWorks. Next slide. Where a tapered I-beam spar was designed as opposed to a constant one, and a finite element model was produced, which is shown on the right. During static cruise, a safety factor of 4 was found. However, this reduces significantly during maneuvers with the load factor in. The final wing structure uses this primary spar in conjunction with the ribs to attach the wing skin. The spar is located approximately at the quarter chord position, which is 38 inches from the tip of the wing. For the spar, 1024 T4 aluminum was chosen for the balance of high strength to weight ratio, as well as fracture resistance. Next slide.
So for the fuel system, it consists of wing tanks and an auxiliary fuselage tank. The wing tanks have a combined capacity of 180 gallons. They are bladder tanks made out of synthetic rubber resistant to punctures. And the auxiliary fuselage tank is the self-sealing type, and it has a capacity of 80 gallons. We decided to go with a fuel pump system with a selector valve separation for the wings and the fuselage tank. The system will filter out the fuel and direct it to the engine, as you can see on the diagram representation on the left. And on the right side, you can see a representation of the fuel bladder under the wing. Next slide.
The ordnance we'll be using on any given mission is outlined here. From the drawing on the right, you can see that there are 3 total hard points underneath each of the wing. Each of these locations carries the various bombs, missiles, and machine guns, and the specs for those can be seen in the chart on the left. Each wing features a FN HMP 400 pod and rail system capable of carrying either 3 2.75 inch air-to-ground rockets or a 50 caliber machine gun. The AIM-9L missile is a short-range air-to-air missile that was chosen for its reliability and just relatively low cost. And then both the MK82 and the GBU-12 are bombs that are going to be used, the GBU-12 being a laser-guided bomb and the MK82 being for more general use. Overall, it's a pretty diverse wing weapon carriage and can feature either a missile bomb or a missile gun configuration depending on what the mission requires. The M621 was our chosen integrated air-to-ground gun, and it is mounted underneath the center line of the fuselage, which is close to the CG, and it does not endanger the nose or the landing gear, which we like. And as far as stealth consideration, the main focus is going to be radar detectability, and for that we have radar absorbent paint. This was chosen instead of using radar absorbent materials because the radar absorbent materials would cause a lot of weight and cost penalties that we didn't really want to endure. And the aircraft, it also helps that the aircraft is relatively small, so this helps with to have a less of a radar signature when dealing with things like radar cross-section. And we also, for stealth, we considered things like infrared, noise, and visibility detection. Next slide.
I'll be going over some of the subsystems on the aircraft. First off, our electrical system. Generator will be creating a 115 volt current signal. This signal will be distributed across the aircraft and converted by a series of rectifiers to a 28 volt DC signal for use with aircraft indicators and displays. Our backup power is going to be in the form of an MPU or a micro power unit, very similar to an APU, which also gives backup power. It's just a smaller, more compact, more fuel efficient, designed by Honeywell. And then finally, there'll be some batteries for mainly used for startup on the aircraft to help get the engine going or the MPU going at the beginning. The pneumatic system will be controlled by an ECU, environmental control unit. It'll keep avionics cooling air and pressurized cabin air to the aircraft. When sources of ground power and air are not available, the MPU will be able to power these systems and give us these capabilities on the ground. Top right is just the operating characteristics for the 115 volt AC signal. It's fully compliant with MIL standard 704F. Next slide, please. The radar was simplified into a single LRU. Thales Group has the Airmaster C system, which has already been proven on helicopters for radar, which flies similar missions to what we are looking to do. Eliminates the need for a transmitter, separate antenna, separate receiver. Just kind of has a nice compact, low weight system for us to use. For radios, we're using a UHF, VHF frequency range with the NR 210 radio. This has ComSec communication security functionality, interfaces with secure computers, and most importantly, it's already used on military aircraft and available in those supply chains, so lower cost to add that. For the flight instruments and navigational aids, mainly things that are already seen on most aircraft: altitude, attitude, airspeed indicators, artificial horizons. We will be using a modern glass cockpit design. And finally, for the navigational aids from Raytheon, there's a GPS-aided inertial navigation system. Combines GPS satellite tracking with inertial navigation system, dead reckoning, and those types of capabilities. Next slide, please.
So once most of our initial design work was completed, we could come in here and actually do a weight estimation of pretty much everything that we could weigh on the aircraft. And as you can see on the table on the left, we included some notable items and their weights, as well as the distance from the datum for the x-axis and the z-axis. As you can see in the figure on the right, the x and z-axis is focused on the nose of the aircraft and at the center line of the propeller. So these weights were pretty much, we got these weights from using OpenVSP, SolidWorks, some weight equations found in the textbook, online sources, or we got them from similar aircraft, or they're either listed in the RFP. Once we were able to determine the weight of each part in our aircraft, as well as their corresponding distances from the datum, we could determine the center of gravity for different states and different loading scenarios, as well as the center of gravity envelope. So as you can see in the figure here on this slide, we have the center of gravity for the design mission at 4 separate loading scenarios. At takeoff, once missiles and bombs are deployed, once most of the fuel was used and empty, and then also once all the fuel was empty and all the missiles were deployed. And as you can see, the weight varies from 11,823 pounds down to 9,123 pounds. And the respective center of gravities for the x-axis are 14.10 feet and 14.79 feet. As you can see on the figure on the right for this center of gravity envelope, there are also forward CG limits and aft CG limits, which were determined by using historical data and kind of just procedures for similar aircrafts. Furthermore, the center of the gravity for the y-axis was negligible because for our aircraft, it was assumed that it was mostly symmetrical about the y-axis.
This brings us to stability. First aspect of stability we looked at was longitudinal stability, about the pitch moment derivative and pitch moment disturbances. So we want a statically stable aircraft. So we were looking for a negative pitch moment with derivative with respect to angle of attack, so that aircraft disturbances would right themselves. So if a pitch down disturbance happened, aircraft would pitch up in response for stability. To do this, we looked at a couple different factors in the aircraft. We found this derivative about the wing, fuselage, tail, And then we also looked at propeller disturbances, which are all outlined in that first equation on the page. The next thing we had to do was also verify a neutral point after the CG. As shown in the last slide, the aft CG limit was 15.13 feet. We found a neutral point to be at 15.2 feet. So it's aft of all of our calculations prior, also needed for stability. And then finally, we analyzed trim conditions. And that graph in the bottom right is showing a number of flap orientations to achieve trim, and trim being the dotted line in the center of the page. Next slide.
Similarly, a lateral and directional stability analysis was conducted. Some of the equations used here for these, for the yaw moment derivative and the roll moment derivative are listed here. And it kind of goes through some of the estimations that are used to get to these values. So for our yaw moment derivative, we're looking for a positive value between about 0.1 and 0.2 based on historical data and similar aircraft. And so we got a good number there. We wanted to verify a negative roll moment derivative, which we did. For our trim analysis, the goal is to maintain 11.5 degree side slip or beta angle while using 20 degrees or less rudder deflection. And using this yaw moment equation, we were able to solve for the rudder deflection as only 5.5 degrees to maintain that condition. Next slide.
So for the takeoff and landing, we can divide both of these processes into ground roll, transition to climb, and then just repeat the process in the opposite direction for landing. We did some calculations done at 6,000 foot altitude, because that is the max altitude required for the RFP. And distances found can be seen in the table. Notably, the total landing distance was less than the total takeoff distance, and the approach distance was less than the climb distance, mainly due to the factors on the ground roll or on approach, such as the no thrust being generated by the engines or very little thrust. Next slide, please.
A performance analysis was made both in the flaps down configuration, which is shown on the left, which is for like takeoff, and then the flaps up configuration, such as cruise, which is shown on the right. The yellow area indicates a positive engine power factor. This area is further reduced on the right, as shown when the load factor increases, which is during maneuvers or turns or anything like that. The case of negative engine power, which is shown in purple, would mean that the engine thrust cannot overcome the drag and thus cannot go any faster. In the case of flaps being deployed, there is added drag, and that's shown on the left, which is the purple being further to the left. And there's also a mechanical limit, which is that blue line, which is associated with the maximum speed that the flaps can endure, basically. The red line indicates the stall limit, or the minimum airspeed needed to maintain flight at the maximum lift configuration. And therefore, the airplane can only operate on the right-hand side of this line. The green line on the right graph indicates the airspeed required for straight and level flight, which is if you wanted to have a completely horizontal plane, which is normal conditions. And this gives a reasonable limit up to 35,000 feet with a maximum speed of 550 feet per second, while still maintaining full maneuverability, or n equals 2 maneuverability. And you can see that that's that green dot on the right-hand side. And there's also a more extreme kind of upper bound, which is the red dot on the right-hand side, while still maintaining n equals 2 maneuverability. Next slide.
So here we have a cost estimation for both the initial flyaway cost as well as the operating / maintenance costs. And the flyaway cost was estimated using a DAPCA4 cost model and then adjusted for inflation. And then on the right, you have a breakdown of the operating costs, and these are assuming 1,200 flight hours. That's what the FH is for. On the next slide, you can see a full breakdown of the DAPCA4 model and how each factor contributes to that cost. And although there was no budget for this design, we tried to minimize costs wherever we could, and the result was actually an aircraft that's cheaper than a majority of similar military aircrafts that you'll find. And that concludes our presentation. So thank you for your time. And at this point, we're going to open it up to some questions you might have from the audience.
Thank you for the presentation, great presentation. Professor Carroll is here. Thank you for coming to support our Group 6. Do you have any comments, any suggestion?
A few questions I just sort of thought about while you were making the presentation. First, it was a nice presentation. I was impressed by how complete your design was. You sort of hit all aspects, even picking weaponry. So, few questions I had. So things like the structural design. So I'm not a structural designer, but I was kind of curious on the factor of safety of 4. How did you pick a factor of, did you pick a factor of safety that you were shooting for, or does that just happen to be the factor of safety that you ended up with?
So I did most of the FEA analysis of the wing spar. And so while I was designing it, I was hoping to get it a factor of safety lower, a little closer to 1.5 or 2 in that area. But as I started getting the spar smaller and smaller, it started getting almost unreasonably small in its dimensions. And I thought it would be better to leave it some room, since it was a pretty cursory analysis of the spar, and leave it some more leeway for loadings during abrupt maneuvers, pulling out of a dive on an attack run, things of that nature, and allow it to be more resistant to battle damage as well.
Okay. How did you define failure?
Failure of the spar.
Yeah. Well, when you define factor of safety, you have to define failure somehow. What was failure?
It the maximum stress over the yield stress of the material, based on our FEA analysis that we found.
Permanent deformation then?
Correct.
Okay. So on the wing itself, in terms of failure of the wing, was it failure of the main spar was the failure of the wing, or was there any other components that might fail first?
We primarily focused on the spar. We didn't take into too much consideration, just based on our time constraints. The other components, we wanted to make sure that we had the spar designed well first, as it's the main load carrier of the wing.
Okay, so I'm curious, maybe some of the other members, can you think of just operationally, would the spar be the limiting factor, or would there be other components of the wing that might under load cause you to fail first?
Well, I would say for sure the skin is also a pretty big factor, because it's going to be on the top and the bottom of the beam in this case. So it's going to be experiencing the most, a lot of the most forces. So it'll have a lot of buckling or tearing issues that can occur there. While a lot of those can occur and they can still land safely and it can be repaired, the spar itself is the main structural component, but there can definitely be a cascading failure where you have something that starts in the skin and then can cascade.
Okay, so the skin, you might tear the skin or
buckle it, yes.
And then it would cause an aerodynamic problem as well. So does the skin carry any of the load?
I mean, sorry, I'll answer this one. It carries all the load, on the bottom mid and the top.
Well, so structurally though, do you count on the skin of the airplane actually helping the spar carry any of the load?
No.
So you don't count on that. You know, like an automobile, there used to be a frame, and now they've gone to these your car that you buy doesn't structurally, there's no frame really. The frame of the automobile actually is the skin. So why don't they build airplanes that way, I wonder? I'm just throwing it out there. I'm curious.
Can I say something?
Sure, sure.
So based on my experience, I feel that for the aircraft, the majority of load, based on the structure type we choose, the monocoque, the majority of load is carried by the spar and rib. So the skin is more like a for the aerodynamic performance. So we don't count on the skin of the fuselage skin or wing skin to carry load, because let's say for the Boeing aircraft, majority of them use the 2027 T4, and the thickness is about like 0.063 inch. It's very thin, and 2024 T4 is not a very strong material anyway. So normally for the most common structure type we use, we normally don't consider that the fuselage skin or wing skin can be responsible for carrying a load.
Yeah. So the skin's simply transferring the aerodynamic load to the main structure. And
yes.
Yeah, and in automobiles, there's also a safety issue. If you make the vehicle really rigid, then the passengers in a crash, they die. They die easily. So they make the cars purposely crumple to absorb energy. So there's other constraints, I think, that airplanes don't have. Airplanes are very weight driven, so maybe this type of construction is a more weight effective. I don't know. But,
yeah, yes, actually it is because of the weight, because we always want to minimize weight for aircraft, and the requirement of weight is like much more higher than the cars. So for using the spar, stringer, frame, and then cover with the skin is like the best way to for the load carrying and also minimize the weight.
Yeah, this might be a more effective for an airplane for weight purposes, and they don't have to worry. If you crash an airplane, you're never going to use it again. So, and the occupants, it's a different constraint. So yeah, that's all the questions I had. It was a very good presentation, very good design. So,
Thank you.
Thank you so much.
Thank you, sir.
Thank you. Professor Tang is here. Do you have any question? You are muted.
Yeah, I heard the part of the talk. I think the presentation is very good. Yeah.
Thank you.
Good talk.
Thank you, sir.
Thank you, sir.
Okay, so now I'm gonna give some comments about the presentation. So overall, really great presentation. I really like the way you communicate with the audience. The slides is very clean, very pleasant to read. And the whole structure is in a logical way. And if I want to be super picky, here are several comments about your presentation. So the first one is on slide, well, you don't have slide number. So the one about the airfoil selection, I think it's probably page 6. Yeah, so for when you talk about the reading that you choose this airfoil for your wing design, and you show this graph of the lift coefficient and angle attack. And what I want to say here that it's like, you'd better show this one in a bigger range, because right now it's only like okay, for the same angle attack, we know that the NACA 6413 has the highest lift coefficient. But if you show the whole picture of this graph, we probably can get some more idea like what is angle attack when your airfoil stalls, right? That is also a very important property when we choose a airfoil, because we want to stall at higher angle attack. And for now, when you only focus on small range, we cannot tell like which airfoil has the better stall property, right? And also for the airfoil selection, is not only about the lift coefficient versus angle attack. We also have the drag coefficient. We want to have to be as low as possible, and lift drag ratio, drag polar. So if I would make these slides, I would make it like to put the lift coefficient, drag polar, lift drag ratio, everything on one slide and then compare. And then it's like more persuasive to say, okay, this is why we want to choose NACA 6413, right? So this is for this slide. And the next one is, sorry about noise on my side. It's a crew station design. So it's page 12. So here you put the setback angle, seating height, and the dimension. And for our crew station design, the most important requirement here is the vision requirement, right? We want what is the over the nose vision, side vision, and to the back, what is the vision? So I think it would be nicer if you can include that what is the vision property capability of your crew station. And on the wing structure, so page 14. So on the figure on the right, there's a displacement versus the moment inertia. So I was just wondering, what is the actual displacement of your design? Anybody? Because right now you just gave a curve, so it's a displacement versus moment inertia, and I don't really know what is the actual displacement of your design.
Yeah, if it's based off of the 0.002 estimate that we had earlier, then it gets out to about 80 millimeters. But I will have to check the SolidWorks finite element model that we made specifically to see the actual displacement that we got. But that was the goal, was to get around 80 millimeters.
Yeah. Okay. Great. So I think it'd be nicer if you can put that information on your slides, because that's like a very important property for your wing design. You can either put like what is displacement of our design, or put a data point like on this graph. Okay, point is our design,
gotcha.
Right? So the next one is on page 17.
Sorry, I can't see the page numbers right now since I'm
okay. So the weapons are here. Okay, yes. So for this one, our project requirement is the total weight should be 3,000. So what is the total weight of your weapons?
Well, it depends on the configuration we're using. It has the capabilities of carrying 3 Mark 82 bombs on both wings, and those are 500 pounds each. So that would end up being 3,000. But different configurations might be less. If we had 1 bomb, 1 missile, and a pod loaded, it would be less than 3,000 pounds.
So I would consider it would be better that you put the capability of your aircraft here. So it's like, okay, if my aircraft carry 3,000 pounds of weapons, it can still satisfy all the requirements like the landing distance, takeoff distance, endurance, range, servicing, everything. So that is a proof of the capability of your design, right? So it'd be nicer if you can put the total weight here. And also in terms of slides, I think this is the only slide I would suggest to to separate the weapons and the stealth consideration into 2 slides. So it's easier for our audience to follow instead of saying, okay, this topic is stealth. It just changes slides. So that is just like presentation in terms of presentation. And on the weight estimation page, so I see there are two empties. The payload, so there's no moment arm or anything. It's like you guys forgot, or is intentionally empty this two space?
So for this table, I kind of just included some of like the notable components, and I should have specified that that was just one component, and then in our actual weight estimation table we have different items for the payloads. So that was just like the payloads was 3,000, and then I listed out each one of the bombs or the missiles, and then I showed the distance from the datum.
Great, thank you. So the next one is the longitudinal stability analysis. So so from this page, I think the most important information I want to know of your design is what is the coefficient of moment of pitchment coefficient, derivative pitchment coefficient with respect to the angle tech. So what is the value here?
That value is negative 0.0225.
Okay, great. So I think it would be better that you can put that value here.
Right.
Yeah, so that is like the most important information for our longitudinal analysis, right? So that is the information that audience want. So I would, and also on the graph, the DCM alpha and the CL on this graph. So you use the flap deflection and elevator deflection, right? So my suggestion is that instead of doing this analysis based on the deflection angle of flaps and elevator, it's better to do it in a way that what is the treatment analysis for takeoff, for landing, for cruise of our design.
Yeah, I can do that.
Yeah, so that is like a suggestion also for your final report.
Yeah.
And sorry, too much noise on my side. On page, no, performance analysis. So I'm still a little confused. What is the purple area and yellow area?
Yeah, so that was my way of representing this access power curve, and the way that they plot it in the book is using an actual curve instead of these two colors, and it was mostly down to just that was how I was able to plot it in MATLAB. There's definitely a better way to do it, like to somehow, or I could solve for that curve, but essentially the purple region you can't go in because the engine isn't powerful enough, and the yellow region is acceptable because the drag is low enough and the conditions are there that it can successfully go. And of course, I think I explained the green line is basically what they want to stay on, the most optimal conditions.
Great, thank you. So basically, the boundary of the yellow area and the purple area is excess power equal to 0 line, right?
Yes. And that's what I have on the left side.
Okay, so what is a vertical line on the left?
I added that because I knew I needed to represent the maximum drag that the flaps had. I actually added this for just this presentation because I knew that with the flaps deflected, there is a maximum airspeed that the plane has to go, that it won't, it'll cause mechanical failure in the flaps. So that's what I was trying to represent with that line.
So that line is actually the maximum speed.
Yes, exactly. But basically past that line, we would expect that the flaps would have some type of mechanical failure.
But if that speed change with altitude?
It would, yes.
Yeah, that's what I feel, because it's more like, yeah, when the density decrease, your speed should, right?
Yeah,
so,
I added that primarily because you would, yes, definitely. Yeah. I was thinking a little more altitude because you would eventually turn off your flaps for takeoff, but yeah, that would change as you go up. And
yeah, so that is probably one small point that you probably want to change in your final report. And also for the part for the graph on the right. So the boundary line is basically like, well, basically from this graph, I can see that the store limit, the service ceiling, and the green line is trim condition, horizontal trim condition. These three lines already form a boundary for the envelope. So actually the PS equal to 0 line, it doesn't matter.
Gotcha. Yeah.
Right?
Yeah.
So probably there's something wrong. I'm not quite sure. Maybe you are correct, but maybe you need to double check. Maybe there's something wrong in your calculation. That's
that might be true. I noticed that it only seemed to affect for like jet aircrafts, because I noticed in the textbook it's mostly a factor once you go really when they're talking Mach numbers instead of feet per second. But I'll definitely go check on that and try to figure out how to do that on float better.
Yeah, great.
We may not even need, as you said, we might just be bounded by our horizontal.
Because that three line already form the envelope, and the PS line equal to 0 line is like it doesn't matter.
Yeah.
So yeah, these are all my comments. Sorry being super picky, but overall great job. I really like the presentation, and congratulations. Any other comments? Any?
Just want to thank you for bringing us through this whole semester. We all appreciate it.
Thank you. Thank you. Well, thank you for your support for your whole semester. So
one quick question. The one of the slides you showed the negative value, the C with the subscript M something. Why is a value not a range? Why is a single value rather than a range of value, negative value?
Is that the roll moment derivative?
Yeah. I'm not an expert of this, but I'm just curious.
Go forward one more slide.
Just this one.
Yeah, so that's our roll moment derivative. Basically for the aircraft to be stable about the longitudinal axis, we're looking for a negative value of that derivative of the roll moment. As far as it being a range, it's a derivative of what's pretty much a straight line. So it's an estimation, but it's pretty decent as far as the methodology.
Okay, thank you.
Sure. So I probably can like add a little bit for that part. So the derivative of pitching moment with respect to angle attack is basically a designed aircraft property. So it depends on where your engine is, about the wing, the moment caused by the pitching moment caused by the wing, pitching moment caused by the fuselage and the tail. So once the aircraft is designed, we have the fixed location of the engine, the wing, the fuselage, dimension, weight, everything, and the tail. The derivative is a fixed value. It has no range. So
We could use it as the design parameter though, if we wanted to maybe use it to design the location of a vertical tail or another stabilizer. It could have a range, and we could decide based on the range what we would choose. But we usually we use it as more of a check for our design.
Yeah, the range is more like given a general guidance for our design. But once an aircraft is designed, that value is a single value, it's a fixed value based on our design.
Thank you.
Thank you. Anyone else has any comments? Okay, great. Thank you for the presentation. Thank you for Professor Carol and Professor Tang to support us today. So I'm gonna stop this one, and I will go to the next Zoom meeting.
Yeah, thank you all for coming.
Thank you.
Thank you, everyone.
Thank you for joining.